Thank you. So thank you everyone for being here today, and a very special thanks for the jury for being here also today and for agreeing to read my manuscript, like Christophe and Francisca. Okay, so my thesis is about quantum algorithms for solving combinatorial optimization in the railway domain. And this is a thesis between the French railway company SNCF and the LIRM. So the story of quantum computing started with the idea of Feynman to build a quantum computer in order to simulate quantum mechanics. But shortly after, the first quantum Turing machine model was designed. And after that, there was many algorithms that were very important for the quantum computing field. And the most, I would say, the most famous one is Shor's algorithm. So the algorithm of Shor is really important. Why? Well, first, because this is an algorithm that provides an exponential speedup compared to the classical resolution. But also it tackles a hot topic, which is the topic of cryptography. So mainly this algorithm enables to factorize integers into a prime numbers. After this algorithm, many others came, and one which is important is the algorithm of Grover, which provides a quadratic speedup in order to look for an element in an unstructured base. So all these theoretical results led to investment in practice, so to invest in building computers in real life. So at the beginning of this century, there were the first prototypes of qubits, which is the quantum information of quantum computers. And even if people were still working on algorithms, theoretical algorithms, such as the algorithm of HHL, which is an algorithm that solves a linear linear system, sorry. Other computer came and almost 10 years ago, the first universal quantum computer was born. And today, we have commercial access to quantum computers. And this is why I've done this thesis between SNCF and LIRM, because now we can try to understand better and to apply quantum algorithms on the real hardware. So the subject of my thesis is exactly design and application of quantum algorithms for railway optimization problems. So let me sketch you the landscape of quantum optimization. So in this landscape, you have two branches. The first one is the branch of exact algorithms, and the second one is the heuristics. So the exact algorithms are algorithms that provide the optimal solution of our problem with a probability that is close to 1 and that does not depend on the instance size. So this is also in the literature called bounded error algorithms, but I decided to call them exact algorithms because I wanted to get as close as the classical optimization landscape as I can. So heuristics are algorithms that does not provide the optimal solution always for general cases. Sometimes we have bounds on this on the quality of the solution that they return, but it's not always the optimal one. So what about the exact algorithms? Well, we have many exact algorithms that are based on subroutines, quantum subroutines. So one of the famous one is Grover search, as I said before, and amplitude amplification or quantum minimum finding, or even the combination of dynamic programming and Grover search can, stems from this subroutine Grover search. We also have, for instance, another subroutine that is really crucial, which is the quantum works. And it leads to quantum backtracking or quantum branch and bound. And then we have the famous quantum Fourier transform or quantum phase estimation, which leads to for gradient computation. But another subroutine that stems from these subroutines is the resolution of linear system, and itself leads to a quantum simplex method or even quantum interior point method. So this was about exact algorithm. Now about heuristics. Well, a large class of heuristics is the class of rational quantum algorithms. And one of them is QAOA, that stands for quantum optimization, quantum approximate optimization algorithm. And besides these rational quantum algorithms, we have also other algorithms such as quantum annealing or quantum relaxation algorithms. Okay, so what have I done during this thesis? Well, first, I worked on rational quantum algorithms, and I tried to find a characterization and good properties of this algorithm, mostly for rational quantum algorithms, but also for the specific case of QAOA. And we applied it to the use case of a railway timetabling problem. Then we worked on the part of exact algorithms, and we specifically work on the idea of combining the dynamic programming and Grover search in order to tackle scheduling problems. And eventually, we worked also on polyhedral robust optimization based on the subroutine of the resolution of linear systems. So I will follow this order for the presentation, and I will focus mainly on the results of the algorithm, quantum algorithm based on Grover search. Okay, so let's begin with the heuristics. So the first thing when we have a class of algorithm that we wonder is what kind of problems can we tackle with these algorithms? And the answer is for rational quantum algorithms is that we can tackle problems and constraints with a function, the objective function, which is polynomial, and where the variables are binary variables. So the principle of rational quantum algorithm is the following. So this is an algorithm that is hybrid. So it alternates between a classical and a quantum part. So the quantum part is the execution of a parameterized quantum circuit. And this circuit is parameterized, well, let's say by a D parameter, D real parameters. And then the classical part is the optimization over those parameters by a classical optimizer. And then we alternate between these two parts to guide the optimization of the initial problem. But we know that because we are dealing with problems that are unconstrained, and because we want to solve real-world problem, a first natural question is how do we deal with these constraints? Well, a common thing to do is to integrate the constraint in the objective function as penalty terms. So, for instance, if I have the initial problem, which is minimizing j subject to the constraint k, then I will, for each constraint, I will define a penalty function, and then I will integrate it in the objective function. So this way, because I want to minimize my initial function, I have to choose the penalty function so that when x satisfies the constraints, the penalty function is equal to 0. Or if x violates the constraint, I want this term to be strictly positive because I choose a penalty values penalty coefficients positive. So this is a way to do so, and we've done it to the railway timetable frame that I will present you just now. So this problem takes as input the customer's demand and the availability of the railway network and the rolling stock. And with that, we want to maximize the satisfaction of the customers, and we also want to maximize the profit of selling tickets to customers. So it leads to a timetable, well, high-speed train timetable. And today, this modelization, so this problem is modelized as follows. So it is an integral linear programming. It has many constraints, many types of different constraints. Some of them are hard, some of them are soft. And the current resolution is done with a commercial solver. So the question is, why did we choose this use case? Well, first of all, it's a really crucial problem for SNCF because this is solved years and years in advance, and then many other optimization problems result from this output timetable. So, for instance, the crew scheduling problem will be scheduled on the timetable found of this optimization problem. Second, this is hard to solve. And thirdly, it is really easy to scale it in time and space. So it means that if we if we take a short time and a short small space, it still have a sense to look at this problem. And because of the maturity of the weak maturity of the quantum computers today, it was really important to have this property. So, as I said, a major stake here is the reformulation of the problem. And just to give you an idea, so if we want to reformulate an instance that is around Paris-Lyon, so about 1 day and 6 stations, it requires more than 20,000 qubits. So it is really huge, and we cannot process it on current quantum computers that has mostly 100 qubits. So this is why we had to simplify it into 2 models. So the first one is the model of a set covering problem, where each element is a customer group. So a group gathers customers that have the same demand on the network, and a set represents an available train. So we want to minimize the number of trains and cover all the customers. But this model is a little bit too naive, and we worked on a second model, which is the following. So it's an extended decoupling problem, where we succeeded in integrating the fact that each carriage has a maximum capacity, and we also tackled the notion of operation costs and selling tickets to customers. So for this second model, which is closer to the real problem, the initial one, we propose 2 reformulations. So the first one is the QUBO one. So QUBO stands for quadratic unconstrained binary optimization, and it means that we want to minimize the function that is at most quadratic without constraints and with a binary variable. And we also propose a second formulation, which is QUBO. So it's QUBO with a polynomial instead of quadratic. So we don't require the function, the objective function, to be polynomial, to be quadratic. And we show that the QUBO formulation outperforms the QUBO formulation, both in terms of number of qubits required for the instance, for the resolution, and also on the quality of the solution. So this was about the heuristic part, and we can see that it's hard to go further without a bigger computer, and that's why we wanted to investigate more theoretical results for problems that are important for railway companies. So this is the second part, so about exact algorithms. Okay, so here we try to solve scheduling problems. So why? Well, because scheduling is important for companies such as SNCF. For instance, we can mention the freight marshalling yards, where carriage of freight are coupled and uncoupled, etc. So before going into the details of this part, I just wanted to illustrate you the difference between quantum and classical algorithms. So there are 3 main principles that have quantum algorithms and that don't have classical algorithms. So they are superposition, entanglement, and measurement. So the superposition means that a quantum state is superposed if it's a superposition of initial or basis states. And the power of it is that you can manipulate with one operation or one quantum operator, you can manipulate an exponential number of states. So this is a powerful property of quantum algorithms, or at least quantum mechanics that we use for quantum algorithms. We also have entanglement. So the entanglement is that if we have one qubit entangled to another, or at least a set of qubits entangled with another, if we operate on the first part of the qubits, then it will directly it will directly change the state of the second set of qubits without applying any operation. And lastly, we have the measurement. So it's a kind of drawback for quantum algorithms. And it's here when we want to extract information. So if I have a superposed state, I want to extract information from it, and then I have to make a measurement. And this measurement will collapse on a state, for this example, I'm working on NV string, so I will have an NV string as an output, of the measurement. And the probability of the measurement is proportional to the amplitude of in the superposed state. Okay, so let me sketch you the algorithm of research, but first I will define the problem. So we have as an output, we have a function that takes an n-bit string in input, and that outputs a binary variable. And we know that there exists only one x such that f of x is equal to 1. And we want to know what is x. So by classical resolution, we can do it roughly in 2 to the n operations, 2 to the n calls to the function if we don't know anything about f. And with Grover search, we can improve this complexity and reduce it with a quadratic speedup. So here is the main steps of Grover search. So first of all, we have to initialize our state, and we use the superposition principle to make a uniform superposition of all our states in the input set. And here at the bottom, I represent the amplitude of each state, which are all equal here because we are in a uniform superposition. And let's say that here is the x that I'm looking for. Okay, so after I have a big block that I will repeat square root of 2 to the n times. And this block is divided in two. The first part is the oracle of f. So this oracle is a quantum operator that marks the solution of the state that we are looking for. So here, the mark process is done by multiplying by -1 the amplitude of the state. And after that, I use the diffusion operator, which increases the amplitude of x because x has a negative amplitude. And then so on and so forth, I repeat this block. And after a certain number of time, which is equal to square root of 2 to the n, I measure the superposed state, and I return the state x that I'm looking for with a high probability if I repeat it correctly, so this number of times. So here we can see that we have the three principles: superposition, entanglement, which appears, it's not stated here, but it appears in the oracle, and measurement. Okay, so it's just to show you a little bit how quantum algorithms work. Okay, so as I said, Grover search is really at the core of many other quantum algorithms. So an important one is quantum minimum finding, and another one is using it's not really called quantum dynamic programming, but it's an algorithm that combines quantum minimum finding and the classical dynamic programming. And this algorithm, for instance, enables to solve the traveling salesman problem in big O star of 1.728 to the n instead of 2 to the n. So this complexity is given by the Elden-Karp dynamic programming. So henceforth, I will use the notation big O star, denoting the fact that I ignore polynomial factors in my complexity. So this algorithm, based on quantum minimum finding and classical dynamic programming, we tried to extend it to scheduling problems. And for that, we had to integrate temporal constraints and also to deal with non-linear objective functions. So next, I will present you the kind of problems we can tackle with this algorithm, and I will describe you this algorithm after. So let me begin with the problem definition. So I will not be the nominal problem of the nominal scheduling problem that I tackle. And what is really important to notice here is that each solution is described by a permutation of n jobs. And I also introduce a set T that will represent the set of starting time. Okay, so because I want to solve my initial problem P with dynamic programming, I need to define it on subinstances. So each subinstance is indexed by two things. The first one is J, is a set of job, and the second one is a starting time T. So I will not opt of J and T, the optimal value of my initial problem, where I only schedule jobs in J and where I start my scheduling at time T. Okay, so saying that, it results that solving my initial problems is exactly finding the optimal value, scheduling all jobs in N and starting at time 0. So I want to compute opt of N as 0 to solve my initial problem P. Okay, so now I will describe you the properties that must satisfy my scheduling problem to be solved with our algorithm. So the first property is the additive dynamic programming across the subset that I will call additive DPAS. So what does it mean? Well, I say that P satisfies this property if for any J, so any subset of jobs and any starting time T0, I can compute opt of J and T0 by computing over all jobs in J, so over all jobs in J. I can compute this term by finding the best concatenation between scheduling all jobs in J without this job and setting this job at the end of the permutation. So this dynamic programming is quite common to solve scheduling problems, but we had to generalize it in order to solve this problem with our algorithm. So here is the second property, which is a generalization of the previous one. So this is called the additive dichotomic DPS. And what is the difference? Well, the main difference is that instead of isolating the last job at the end of the permutation, here we will split into the set of job J, and we will find the best concatenation over all sets of jobs X, such that X has a cardinality equal to J divided by 2. Hence the name dichotomic. Okay, so to compute opt of J and T0, I compute the best value of X for any X. So the best value of the first part of the permutation, and then the second one, and I find the minimum of the best concatenation of the two permutations. And here we can see that sometimes there are we can introduce a term beta to express the fact that those two permutations cannot be concatenated. Okay, so let me show you these two properties on an example. So here we are dealing with problems that have one machine and n jobs, and each job is defined by a processing time, a wait, and a deadline. So the processing time is the time to process the job. The wait reflects the priority of the job, and the deadline is a time after which it is not if the completion time of the job is larger than the deadline, then we say that the solution is infeasible. So we want that the completion time to be smaller than the deadline. So the problem is the following: we want to minimize the weighted sum of completion times, and we want to satisfy the constraints of the deadlines. So because we need to define the recurrence on which we will solve this problem, we introduce the set of starting time t equal to the set of integers between 0 and the sum of the processing times, the total sum of the processing times. And we define for each j and t, we define opt of j and t equal to minimizing the weighted sum of the completion times. But here, in this case, the completion time is the completion time of the initial scheduling plus the starting time of the permutation. So we shift all the jobs by t, which is the starting time of the scheduling. And also in the constraints, it appears the same effective completion time. So the completion time shifted by t. So we can show that both additive DPS and additive dicotemic DPS formulation are satisfied. And what is important here is that we can compute the starting time of the second permutation because it's always the starting time of the first permutation plus the processing times of the first permutation. So let me show you an example here. So if we consider the set of job j equal to 1, 2, 3, 4, and for instance, I depicted a permutation where x is the set of jobs 2 and 4, and the left job are 1 and 3. And here for this permutation, whether this permutation is 2 and 4 or 4 and 2, it will always be the same starting time for the second permutation. So we can see here that the starting time of the second permutation does not depend on the optimal solution of the first permutation. It only depends on x. And this is really important if we want to derive our dynamic programming. But unfortunately, this is not always the case. And we have to find other dynamic programmings for other type of scheduling problems. So next, I will present you the second class of problems that we can tackle with our algorithm, which does not satisfy this convenient property. Okay, so let me begin with the counter examples. So we still work on one machine and n jobs, and this time each job is defined by a processing time, a release date, and a due date. So a release date is the time from which we can schedule the job j. And the due date is here to say if a job is late or not. So if the completion time is larger than the due date, then we can say that the job j is late. And in this problem, we want to minimize the sum of late jobs regarding the release date constraint. And here we have a problem. We cannot use the previous properties because we don't know always the starting time of the second permutation because of the release date constraints. Because here we can have blanks, and now the starting time of the second permutation depends on the optimal solution and not only on the set x that we are looking at for the first permutation. So this is why we had to define another dichotomic DPS recurrence. So for that, we slightly changed the problem on which we are deriving the recurrence. So we will require an additional index epsilon, and we define opt of j, t, and epsilon as the minimum make span, so the minimum larger completion time, where exactly epsilon jobs are late. So here we will use the dynamic programming not on the natural problem that derives from P, but a slightly different problem. And with that, we can deal with these release date constraints because here the starting time of the second permutation is exactly the optimal solution that we compute for the first part of the permutation. So this is a way where we can, thanks to that, we can deal with the release date constraints. Okay, so I presented you two classes of scheduling problems that can be solved with algorithm. So now I will present you our algorithm. Okay, so this algorithm, as I said, is based on quantum minimum finding. So this the quantum minimum finding takes as an input the function f and computes the minimum of f in big O of square root of the cardinality of the input set. So the square root really comes from Grover's search. So our algorithm is as follows. So it is a hybrid algorithm. So it alternates. It has a classical part and a quantum part. So the classical part is the following. So for each set of job x of size n/4, and for each t prime, any starting time, we will compute opt of x and t prime by classical DPAS. And let's say that for the description of the algorithm, we deal with scheduling problems that satisfy additive DPAS and additive dichotomic DPAS. So we will use classical additive DPAS in order to compute each opt of x and t prime. So this is the classical part. And then the quantum part is the following. So remember, we want to compute opt of n and 0. So we will do that with quantum minimum finding applied on the dichotomic DPAS version of our property. So we will have something like that. So opt of n and 0 is equal to minimizing over any set of job of size n/2 of terms that are opt of j and t, where j is of size n/2 and t is any starting time. And then in order to compute those terms, we apply recursively quantum minimum finding on also the same property, which is the dichotomic DPAS. And then we will have something like that. So opt of j and t is equal to minimizing over x of size n/4 this time. So minimizing, yes, these terms, where x here is of size n/4. And because we computed these with on the classical part, we can compute the overall result. Value. Okay, so now what about the complexity of this algorithm? So the classical part is done with this complexity, which comes from the classical dynamic programming complexity. And you can notice that if we wanted to apply the classical dichotomic, the classical DPAS version to compute this term, we would just like to take k equal to 1 to n, and it would give 2 to the n. So it's really the same idea as L and so this complexity is equal to big O star of cardinality of t, because we compute opt for any t, multiplied by 1.754 to the n. So what about the quantum part? Well, first we apply quantum minimum finding to this equation. So the complexity is equal to the square root of the cardinality of the minimum. So here it's n/4 among n, multiplied by the complexity of computing those terms. And this is done recursively by using also quantum minimum finding. And here we are looking for on a minimum of a set of jobs of size n/4. So this time it's n/4 among n/2, so the square root of it, multiplied by the complexity of computing these terms. And these terms are always already stored in the QRAM, so the complexity is constant, or at least polynomial in the instance size. So the complexity of the quantum part results in 1.682 to the n. And the total complexity of this algorithm is the maximum of it. So here, this is the classical part that has a bigger complexity. And we can say that our algorithm solves the initial problem in a big O star of cardinality of t multiplied by 1.754 to the n. Okay, so on the examples, we can see, so we can compare it to the best known classical algorithm complexity. And each time, the exponential part is reduced in our complexity algorithm, but sometimes at the cost of a pseudo-polynomial factor. And one can mention that this algorithm can be adapted also for decision problems, and I will just prove it to you on the 3-machine flowchart problem. Okay, so let me introduce you quickly this problem. We have 3 machines and n jobs, and for each job, we have 3 operations. So operation 1, operation 2, and 3. and each operation must be proceeded on just the number of the machine it represents. And what is important here is that each operation must be proceeded in this order. So a job must be proceed on machine 1, then machine 2, and then machine 3. So this constraint results in the fact that solution is a permutation of n. And so I just depict you here an example with 3 jobs. So for instance, I represented the permutation job 1, job 3, and job 2, each one with a different color. And here, the optimal solution, well, the cost of this permutation here is the max span, the total max span of this scheduling, which here is equal to 12. Okay, so the question is on which problem will we apply our recurrence? Well, for that, we have to define a decision problem associated with our initial problem. So it is defined as follows. So for any j, beta, and epsilon, we define this decision problem as follows. So that there exists a feasible solution of job in j such that it holds between the 2 temporal fronts, beta and epsilon. So we want to know if there is a solution where each operation begins after beta and ends before epsilon. So this is the problem on which we will apply the recurrence. And then the recurrence is the following. So for instance, I will take the dichotomic version. So to know the value of the decision problem on j, beta, and epsilon, we find this value by iterating over any x of size n j over 2, and for any temporal front between beta and epsilon. And we will ask the question if there is a feasible, well, if there is a permutation that holds between beta and t for the first part of the permutation, and then for the second part, if it holds between t and epsilon. So this is really a DPS recurrence that can be applied to our algorithm. And see if we replace quantum minimum finding by Guerrero search, because here we are looking for a true value and not for the minimum of a function, we can reduce the complexity of solving the 3D machine pressure problem. Okay, so let me end with the robust part of the thesis. Okay, so we know that in the problems of railway companies, there are uncertain data. And for instance, I can mention if you have an incident on the network, or if we broke a catenary, or if we have we don't know the dwell time of the trains on the platform, etc. So we have a lot of problems with a robust, uncertain data, and that's why it's important also to look at robust problems, robust optimization problem. Okay, so the problem that we worked on here is the following. So we want to minimize on a feasible set y, we want to minimize the dot product between the cost vector c and the decision variable y. And the robust counterpart that we looked at was where only the cost vector was uncertain. So here it is represented by the fact that we minimize over y the maximum deviation of the cost vector that we can have. And here we say that the deviation c lives in the polytope c. And this polytope is described by a matrix and a dimension, etc. So the classical resolution of this problem, one of the classical resolution is to solve a bunch of linear system to define other problems on which we will apply the resolution of this initial problem. So I will explain it. So we want to solve a big O of n power to the s, where s is one dimension of the polytope. And for each problem, well, each problem is defined by a solution theta of a linear system defined by the matrix A. So those linear systems depend on the matrix A. I didn't write properly all the linear systems, but it really depends on the shape of the polytope. So we say that, in other words, solving the initial problem amounts to solve over all linear system a new optimization problem where the objective function depends on the scalar product of the solution theta of a linear system and other elements that describe the polytope. So the classical resolution of this problem is as the following complexity. So in order to compute these terms, we need to solve this linear system. So we will call G this cost. And then for each linear system, we also have to solve this problem. So we will call F this complexity. And then because we have to do that for any linear system, well, we multiply by the number of linear systems we have to solve, which is equal to n per S. So because we wanted to improve the complexity of this resolution, first idea was to use the subroutine of quantum minimum finding in order to reduce the complexity of computing this minimum. So it results in a quadratic speedup over the number of linear systems that we need to solve. And another idea was to use quantum linear system algorithm, which stems from the algorithm of HHL, but it's a new version by HL, in order to compute the terms, the scalar term, with the solution of each linear system. So it will impact the complexity of J, but because there are precision parameters that come into account, and because also there are errors that are introduced with this quantum subroutine, today we didn't find any advantage using this quantum subroutine. Okay, so let me conclude this presentation. So we really worked on at different levels in the quantum optimization landscape. So the first one was heuristics. So we characterized the class of variational quantum algorithms, and we really applied it to a real Ray use case. We also dealt with exact algorithms, so both for scheduling and for robust optimization. So this is what have been done. And now what about the perspectives? Well, for the heuristics part, we can think of going further in the investigation of comparing the Cubo and Cubo formulation. So maybe trying other problems and understanding deeply how it works. And we also, unfortunately, we also have to wait for more mature machines in order to see the really understand and quantify the performances of these algorithms. So about exact algorithms, we would like to extend our algorithm to other scheduling problems, for instance, the job shop. But we could also think of investigating other exact algorithms that use dynamic programming, for instance, inclusion, exclusion, etc. And for robust optimization, well, first, we would like to find maybe tighter bounds, because we are not sure that the analysis that does not improve the complexity is tight. And we also we would also like to characterize the uncertainty set, because I didn't mention it, but in order to use the quantum algorithm that solve linear systems, we have to make assumptions in the polytope to solve it with this algorithm. So maybe trying to characterize this set is a future work. So thank you very much for your attention.